Okay, so we've developed a way of describing all of the different forces that are acting on a material element. We've recognized that there are body forces, there are surface forces acting over the surface, and there may also be at boundaries line forces. And we want to put that all together and develop a conservation equation, in this case a conservation equation for linear momentum. So we're going to be interested in thinking about the momentum of a material element. And the equation that we're going to derive is usually called the Koshi momentum equation. An important thing to recognize is that actually this is going to be valid for any deforming material. It might be true for a fluid, but the equation that we'll derive will also be true, at least to start with, for a solid as well. So what we want to do is we really want to think about just simply applying Newton's second law. So we want to apply conservation of momentum through Newton's second law. Which we're going to think about as applying in the form that we really want to think about the mass times the acceleration is the sum of all of the forces acting on our material. We also know something about conservation of mass. We've thought about conservation of mass already, so we've also got that equation. But here we're going to be thinking about a vector equation. And we want to write this, though, in terms of the things that we've thought about in terms of an Eulerian description. So we're going to apply Newton's second law on a per unit volume basis. Eventually. Okay, so that's what we'll head to. And so let's think about writing down the different terms that we might have on the left-hand side. If we're interested in accelerations, then we're going to be interested in the mass of our material element, which will be given by the volume times of each little material element times its local spatial density. So rho is the local density. So we can write this as rho. We'll multiply it by a volume element dv. And then we need to write down an expression for the acceleration. And we've seen a way of describing acceleration. We would think about acceleration A in a Lagrangian framework. But if we are going to be interested in following the acceleration of this little material element of fixed identity, then we know that the equivalent statement of that in the Eulerian framework is to write it in terms of this idea of the material derivative of the velocity. And so our Eulerian description of this is going to be in terms of dv by dt. So here's the mass per unit volume multiplied by the volume times the acceleration, and that has to be given by all of the different forces that we know are acting on the system. So the first thing that we might think about is we might think about the surface forces that are acting over this volume, and we know that the surface forces are written in terms of a traction vector, n dot tau, and then we're going to need to integrate those over the entire area multiplied by the area dA. And so this is a vector. It's a vector integrated over an area, and it's going to be equal to the vector, which is the acceleration. So that's one contribution. And then we're also going to need all of the body forces that are acting on it. So the body forces acting on our little material element will be rho g dv, where our little body force, remember, acts through the center of gravity, depends on the mass, and it will be multiplied by g. One important thing on signs, we'll write this for now in terms of a general vector quantity g. It's very common in many problems that we'll see that we'll actually define g as having a magnitude, 9.81 in the SI units, and typically we usually think about gravity as pointing down, so frequently we'll rewrite gravity this way, but for now we're going to keep things absolutely general. And so if I integrate this over all the volume, then that is now an expression of F equals ma for our entire system. And so this is, in some sense, a conservation of momentum equation, but we'd like to try and simplify this. And the first thing we recognize is that two of these integrals are volume integrals. The other one happens to be an area integral. And so we'd like to convert this into a volume integral, and we know how to do that using this idea of the divergence theorem. So we can apply the divergence theorem to convert this from this into something that, of course, we should imagine is going to have del dot tau in it. And so let's do that, and we're going to then do that, and then we'll see that, in fact, everything can be written in terms of volume integral, and we'll gather all of the things on this side of the equation. So we might write this as rho dv by dt. This will become a divergence term. I'll bring this over this side, so this would be minus the divergence of the stress integrated over the volume. And similarly, we'd write this as minus rho g. And this whole quantity is integrated over the volume, and now nothing else is left on this side, so we're left with 0. And so there's another statement of conservation of momentum. And the thing we can recognize is that we've done this for an absolutely arbitrary shape or an absolutely arbitrary volume. So this could be true for any volume. It could be true if I cut the volume into a different shape or a different size. And so the only way this can be true and equal to 0 if it's an arbitrary volume is if this quantity, what we would call the kernel, what's inside here, is identically equal to 0 for every single material element. So this must be 0 for every arbitrary volume. And so I can keep doing this for any different volume I like, and in fact I can shrink this to be a smaller and smaller volume until we're just thinking about this applying on just one of our tiny little material elements, and this must be true equal to 0 for that. And so in fact it's true that it's 0 everywhere, and so we can just write the equation in terms of this being equal to 0. And so this equation we'll write in this way. If this is equal to 0, then I can write it as all equal to 0, but it's maybe clearer to bring it across this side and write it this way, so that on one side we just have mass per unit volume times acceleration, and on the other side I have all of the forces acting on it, and we recognize that the forces are coming from both surface forces and from body forces. Okay, so we have now an equation, and this was derived by Koshi, and so it's called the Koshi momentum equation. And we haven't assumed anything about the state of our material except that it's a continuum. So you can actually apply this to a solid, you can apply this to a fluid, you can apply this to a gas. But it's actually kind of hard to apply this at the moment for the following reason. We can think about what's unknown. And in general, we have a velocity that's unknown. That will have 3 components, so x, y, and z. And then we also have a stress tensor that is unknown. One thing we do know about the stress tensor is we know that it's symmetric, or we expect this to be symmetric. So we would expect tau would be equal to tau transpose. So that's maybe good, but that still gives us 6 unknowns. So we have 6 unknowns plus 3 unknowns for the velocity, and we'll assume that we know the density of our material. So we have at least 9 unknowns to think about. And the problem is that we only have 3 equations. This is a vector equation, so we only have 3 equations in at least 9 unknowns. So we're underspecified. So we really can't go on and do anything more about this until we say something about how tau is related to other variables in the problem. And that's an example of what we will come back to, and what would be called a constitutive equation. And we're going to need to specify that before we can go on much further. So we'll do one very simple example of a constitutive equation that we do know already, and that will make this equation a little bit simpler. So the simplest equation that we know so far is we've seen for a fluid at rest, we've seen an expression for this. So for a fluid at rest, which has no viscous stresses at rest, we know there are only normal stresses, and so we've written that tau is equal to minus p times I, where p was our isotropic pressure. Pressure was defined as facing inwards, and so the stress tensor would be given by this. And when we say that there's no viscous stresses, people will often refer to this as an inviscid approximation. And so if we don't have any viscous stresses, then this becomes a lot simpler, and we can substitute in terms of our equation for del dot tau as being equal to taking the gradient of a constant scalar, p, multiplied by a tensor I, and so this just becomes minus the gradient in the pressure. That's an exercise that you can work out by just combining the idea that the unit tensor is just a constant, and then the only way I can find a vector is that it must be the gradient of a scalar. So if we combine this with this statement, then actually we get a much simpler equation, which looks like rho dv by dt, mass per unit volume times acceleration of a material element using this idea of a material derivative, is equal to the divergence of all of the forces acting on the surface of this. The divergence of all the forces is given in terms of a force per unit area, which is a stress. The stress happens to be only inward pointing pressure if there's no viscous stresses, so that becomes minus the gradient of the pressure. And then, of course, there's also the body force acting on our material, so we end up with rho g. And so this equation has simplified. And this equation is a simpler equation that is known as the Euler equation. So this is a German name named after Leonhard Euler, so it's pronounced Euler. And you can see how things are simpler now, because we still have three unknown components of velocity. But now we only have one unknown component, which is the pressure. It's worth bearing in mind that pressure can be a function of position and time. But we take the gradient of it, and it's gradients of pressure that are important. And then, of course, there's body forces. Now, if you're paying attention, we might recognize that we say, well, actually, that's still a problem. We've got one unknown here and three unknowns here. So we have four unknowns, and we only have three equations here. And so we'll also need to combine this with a statement of conservation of mass. And we've derived an expression for the conservation of mass, that at least for an incompressible flow, we would say that the divergence of the velocity is zero. So this is conservation of mass for an incompressible fluid. And so now we have another equation. We have one scalar equation plus three vector equations. We have four equations and four unknowns, so it looks like we're in very good shape now. And this would be, in general, the set of equations that you would solve for an incompressible and inviscid fluid.